So, going back to the octet rule with Lewis structures, if I had lithium and I have sulfur, to actually add on to the octet rule, elements will lose, gain, or share in order to have full valence shells, or 8 valence electrons. So in the case of lithium, lithium only loses 1. And we can see this when we look at the ionization energy of lithium being relatively low. I should indicate that that's the first ionization energy, the energy to lose 1 electron. However, second ionization energy, the energy to lose a second electron is really high. Because for lithium to lose a second electron, it would no longer be stable. Sulfur, on the other hand, has high ionization energies. And in fact also has a relatively high electronegativity. So it prefers to gain 2 electrons. And has a 2 negative charge. Now, looking at an ionic bond, we know that ionic bonds tend to happen between metals and nonmetals. So ionic bonds are always the type of bond where there is electron transfer. That means that one element donates its electrons to another element. So ionic bonds tend to really only happen between metals and nonmetals. So for instance, if I were to take sodium and chlorine, like other metals, sodium wants to lose electrons. Nonmetals tend to want to gain electrons. Metals have low ionization energies, so they easily have their electrons taken by another element, while nonmetals have high ionization energies. Metals have low electronegativities, and nonmetals have high electronegativities. So if we look at sodium, which has 1 valence electron, and chlorine, which has 7 valence electrons, you can easily see how sodium will give 1 valence electron to chlorine, so that sodium has a positive charge, chlorine has a negative charge. And I should show that in this case you can see that chlorine then has its full valence shell, this completed Lewis structure. To show what that looks like in terms of electron configurations, we know that sodium has 1s2, 2s2, 2p6, 3s1, and chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So by taking away that 1 electron from sodium, it now has the same configuration as neon. However, it still has the same number of protons, 11 protons, now 10 electrons. Protons being positive, electrons being negative, 11 positives, 10 negatives, gives us a net charge of 1 plus. If we look at our chlorine, we can see that if it gains 1 more electron, it now has a configuration similar to hold on. I can't see my periodic table from here. It now has a configuration similar to argon. Remember that it has 17 protons, again, that are positive, but now with its new configuration, it has 18 electrons. So a net charge of 1 negative. Now, earlier we saw that when electrons are taken away, there is ionization energy involved. So there is some energy necessary. If we look particularly at sodium, we can see that it takes 496 kilojoules per mole to remove 1 electron from sodium. Chlorine, on the other hand, releases 349 kilojoules when it gains 1 electron. So when an element becomes more stable, it has less potential energy. In this case, oddly enough, taking that electron away from sodium does make it, to some degree, more unstable because it is now an unbalanced charge, a positive charge with a negative charge. So if we were to look at this net change here, this would actually seem to be an endothermic process, and a reaction that actually requires energy. However, these two ions, this now positive ion of sodium and this negative ion of chlorine, which are kind of unstable on their own, become more stable together. So once they have sort of, in effect, canceled the energy, what we get is a release of 788 kilojoules per mole. So this also, if we look at this another way, this is also, if I were to say put in 788 kilojoules per mole, that means I could take NaCl and split it into sodium and chlorine ions. So this energy that it takes to separate the ions in an ionic compound, which is usually quite a lot of energy, is called the lattice energy. So it's the energy to separate ions in a lattice configuration.